Hi, I'm Tony Tamasi with NVIDIA, and I'm here to talk to you about ray tracing and DXR. So ray tracing introduces some new technologies to the graphics pipeline. These are some of the fundamental techniques and building blocks that makes ray tracing possible. A BVH is an acceleration structure or a data structure that makes it possible to do high-performance ray tracing into a scene in real time. Ray triangle intersection is pretty much exactly like it sounds. You shoot a ray into a scene, you decide whether or not it intersects with geometry, triangles, and then what you do with it. Does it reflect? Does it terminate? Is it blocked or occluded by things between it and the light source? And that lets you do things like reflections or shadows and things of that nature. The ray tracing results in what might look like a grainy image, and so we do a thing called denoising, where it takes that somewhat grainy image and polishes it to make it look like the perfect final picture. A common graphics effect is called ambient occlusion. That's that kind of darkening that you get in the cracks and crevices in games. You shoot a fairly large number of rays, but in a fairly local region into the BVH. So while there's a lot of rays, because they're not doing a lot of bounces and they're in a small region, the performance impact for ambient occlusion can be relatively low. This is a really nice subtle effect that provides kind of a grounding to objects and scenes and brings out the depth of a scene. Shadows are one of those other effects that are really common in games. Ray trace shadows take rays and shoot them into the scene for every light source and intersect with all the geometry. An occluder is something that blocks that light source. And if you shoot a ray and it's blocked by the light source, well, then that means that you're in shadow. Shadow of the Tomb Raider, for example, can have a large number of light sources and is a rich geometric world. So the performance cost for ray trace shadows can vary quite a lot. Ray trace reflections are one of the great advances from a computer graphics perspective because the classic techniques that we've done in programmable shading have always fallen short. Ray tracing reflection solves for all of that by tracing rays from the surface globally into the scene to compute the proper result on that pixel. What we have as an example here is Battlefield 5, which has implemented a really clever technique to know which surfaces have reflective properties, trace more rays from the surfaces which are more reflective, and less rays from the surfaces that aren't. What that allows them to do is deliver the ray tracing reflections kind of where it matters, which lets them deliver a really great result while still delivering a really good frame rate. So ray tracing is not only possible to kind of improve on effects that you've seen before, it's also possible to do things that just really weren't practical before. In this example, you basically have the classic hall of mirrors, but in this case, one of the mirrors is actually entirely off camera. So not only are we reflecting from that mirror that's off screen, but we're actually doing recursion, which means bouncing those rays between the mirrors to get that infinite mirror effect. Global illumination is one of those kind of holy grails in graphics, and particularly the way to do that in real time. The folks that developed Metro have implemented a technique to do 1 ray per pixel for global illumination, which allows you to kind of gather the light from the whole world and scene and compute it correctly for each pixel. Produces a really nice quality effect, really pleasing, really soft kind of natural lighting. So we've talked about a number of ray tracing techniques. They all have different characteristics. The mileage will vary greatly between technique, implementation, and game. Game developers are free to choose how they want to implement this and the degree that they want ray tracing to be pervasive in their game. For example, in Battlefield 5, they're still doing ray tracing, but just less of it. On a high-end Pascal like a 1080 Ti, you might even get playable frame rates. But for a game like Metro, which is doing global illumination, that's a considerably heavier weight operation, and even on a high-end Pascal, it's probably not going to be practical. But the great thing is it's all being delivered through DXR, so even folks who have Pascal, if they just want to check it out, they can at least see what ray tracing looks like and get a little taste for themselves. What we have here is we've captured some statistics from the game Metro, and we've analyzed the behavior of that on a variety of GPUs. So what you see on the top there is a Pascal GPU, a high-end one. It's a 1080 Ti. This is running DXR, software ray tracing. That kind of long, gray, horizontal bar that you see there is ray tracing workload being run on the SM, or the streaming multiprocessor. So you can see that 80% or so of the frame time for Metro on a Pascal is taking up doing that global illumination ray tracing calculation on your shading core. What you see below there is Turing, in this case an RTX 2080. The shader in Turing, though, is considerably more advanced in that it can execute floating point and integer instructions at the same time. That purple section is the integer instructions being simultaneously issued along with the floating point instructions, which makes Turing much more efficient just in general. But it's still not efficient as pure hardware. And so if you look at the bottom, you see that green spike. What that is Turing's RT core, and that's where you get those billions of rays per second, or that gigarays class of performance. An RTX 2080 spends about 1/10 of the time ray tracing as a Pascal architecture, and that helps to deliver that frame time. One other obviously advantage that Turing has is it has tensor cores for doing high performance AI processing. And so that's tensor core activity doing AI processing for DLSS, or deep learning supersampling, which allows you to render fewer pixels but display a much higher quality result. So the combination of RT cores and tensor cores delivers kind of that next generation experience, and this is an example of the actual frame time analysis in Metro that shows that.